Okay, welcome back to our discussion of entropy. So we've defined entropy and thought a little bit about heat engines and um, how you use entropy to understand those. Now we're going to talk about how you measure or calculate other processes' entropy. Okay, before we do that, I needed to make a clarification. We finished the last lecture talking about heat pumps and refrigerators, and I incorrectly circled this QC. So when you take some heat out of a cold place, like the inside of your refrigerator, that's a value. But the heat that you throw away outside your fridge can't be equal to the heat you took out of here, because if that was true, then because T cold is smaller than T hot, it would always be a negative entropy. So the only way to make it positive is to change this Q. So rather than this Q being just QC, it has to be QC plus the work. So when you put work into your refrigerator, that can dissipate as heat. And so now you can add more heat to what you're throwing away to the hot place. And essentially that's how this term gets bigger than this term, which is negative. The positive term needs to get bigger. So correct that in your notes. Sorry. So now we're going to move on to topic 3B. So we're going to talk about just how do you calculate the entropy changes for different processes. So let's do this. So when you have a change in volume, we know the entropy changes because the isothermal expansion of a perfect gas is spontaneous. So that must mean that the entropy is changing. So if it's isothermal, we'll go through and calculate or derive the equation. But it's also true, entropy is a state function. So if both the volume and the temperature change, you can measure those changes or the entropies, those changes impacts on entropy as a two-step process. So let's say volume and temperature changed. You could calculate how much the entropy would change for the volume change, and then add to that a calculation for the temperature change. And we'll have equations for both of those. So even though this seems restrictive that it's isothermal, it would just be one of the steps in a calculation for both volume and temperature changing. So if we have a perfect gas and we want to look at how the entropy changes in an expansion, if it's a perfect gas, isothermal means the temperature doesn't change for a perfect gas, then internal energy doesn't change. So 0 has to equal Q plus W. So Q has to equal negative W. Because ds is dq reversible over T, I never mentioned up here if I was doing this for a reversible or irreversible process, and it doesn't matter. All that matters is you know the temperature it took place at and the two volumes, because you have to find a reversible path to carry out the process if it's irreversible. And so this equation we derive will be valid for however the volume changes in a reversible or irreversible process. So work was negative nRT ln of V2 over V1 if it's reversible. And then if we change the sign and divide by T, you end up with Q being this. And because it's Q divided by T, the T cancels, and the change in entropy is nR, gas constant, times the natural log of the volume change. So natural log of the volume change, if the volume goes up, is going to be a positive number. If it goes down, it's going to be a negative number. So an expansion will always increase the entropy. Okay, so let's look at this first self-test. And it says evaluate the change in entropy right here, evaluate the change in entropy when the volume occupied by 1 mole of gas molecules increases isothermally by a factor of 100. So we use the equation that we just derived. Volume 2 equals 100 times volume 1. We have 1 mole. If we put in the gas constant in joules per K mole, we'll end up with units of joules per K for our entropy. So 1 mole times the gas constant times the natural log of V2 over V1. And if it's 100 times bigger, then you're going to take the natural log of 100, and you end up with a positive entropy change of 38.3 joules per K. So notice they didn't say it happened reversibly or irreversibly. It doesn't matter. We know the volume change, and that's all that matters in order to determine the delta S. Didn't even have to know the temperature because that canceled. It made Q bigger, and it also made the denominator bigger, but those two will cancel as we derive that equation. So you can also calculate a change in entropy for a pressure change at constant temperature, because at constant temperature, PV is constant, and so the volume ratio equals the inverse of the pressure ratio. So you have a very similar equation, except you put P1 over P2. So you could calculate the pressures, but if the ratios are equal to each other, you don't have to waste that time. So that would be for the volume change. So now if the temperature changes, you might have to add another calculation. So delta S, so the heat capacity is dQ over dt. That's what the heat capacity is defined as. So this right here can be defined as C times delta T. Just take the delta T over here. So I replace dQ reversible with C dt, and then entropy is still defined as over T. So we have to integrate this. And notice it's the same integral we did when we derived the equation for work for a reversible perfect gas. So C would come out front if C is constant. And then the integral of dt over T is just ln of T. So we end up with change in entropy is C, the heat capacity, times the natural log of T2 over T1. Once again, heat capacity is always positive. So if T goes up, entropy goes up. And if T goes down, entropy would be a negative number, entropy change. So yes, so depending on your circumstances, this C would either become CP if you carry out the process at constant pressure, or CV if you carry it out at constant volume. So you can take this general equation that just says he or C, and if it's constant pressure, you know that's CP, and if it's constant volume, you know it's CV. So let's look at the next self-test. 3B.2 on page 95. To what temperature must the same system be heated for the overall increase in entropy to be 1 joule per K mole? And so the system is given above, where it gives you the heat capacity, and hydrogen gas is what we have, and they want the molar entropy. So for hydrogen, the CV is given. You don't even have to look it up. So the problem tells us that it's hydrogen gas, and that the CV is 22.44 joules per K mole. Temperature 1 is 20 degrees. The whole entropy changes by 1 joule per K mole. So I can plug that in for delta S. I can plug in the molar heat capacity, and then I can take the natural log, and I'm solving for what temperature must my system change to in order to have this entropy change. And when I solve for it, move this over here, and then if I raise E to both sides, E is the inverse function of natural log, so that will get rid of it, and I end up with 306 Kelvin or 33 degrees Celsius. If C is not constant over the range, we couldn't have done this integral right here. We can't take C out of the integral. You'd have to either integrate over it if you know the functional form, or you might have numerical data, like you might have measured heat capacity at different temperatures. And as of right now, I'm planning on doing a lab week 2 where you do that numerical integration. And I think I'll do that, but I have to make sure, and if not, you won't be accountable for that. So let's look at the next self-test. For metals, it says, let's see. Well, here's a fairly good picture. Heat capacity can change with temperature, and then entropy is Cp over T. So that's essentially what you're graphing when you might do a numerical integration. So this self-test says for metals, there's a contribution to the heat capacity from the electrons, which is linearly proportional to T when the temperature is low. Write an expression for its contribution to the change in molar entropy at low temperature. So they are saying that, so they are saying, here's our definition of ds, dq reversible over T. dq is C dt. And now when we integrate that, we get delta S on the left-hand side, but they're saying that C is actually equal to a constant times T. So we replace this, which is a function of T, and they say it's linearly proportional to T, so that means it's a constant times T. So that will cancel the T's top and bottom. And so when I take the integral of a constant times dt, I get a constant delta T. And so that is, so the change in the heat capacity, let's see, constant times T2, so C2, so the heat capacity at T2 is equal to a constant times T2, and the heat capacity at another temperature is that same constant. So when you look at this integral, it's actually going to be equal to, so this is delta C P molar, because the constant times T2 minus T1 is how the heat capacity changes, and that ends up being equal to delta S for this problem. So you can have lots of different functional forms for the heat capacity and how it changes with temperature. And when you have a different one from what we've already used, you have to go back here. You have to go back and reintegrate, taking into account that C is a function of T, and then figuring out how that function integrates when you divide it by T. So from those first two equations, you could calculate any entropy change for a volume, pressure, temperature change, because you could say the pressure changed. Well, and the temperature changed. So first let's hold the temperature constant and use the equation for how pressure changes at constant temperature to calculate that contribution. And next, let's change temperature holding pressure constant, and that will give us Cp ln of T2 over T1. So you can use those two equations together, because you can think about changing P and T or V and T in different steps, because entropy is a state function. So if you have a phase transition, they're reversible at their temperature at which you say it's melting, boiling, or sublimation. So that means it's actually an equilibrium process. But if they're reversible, then delta H is QP. So if it's a constant pressure process, QP equals delta H at the temperature at which it boils or melts. So in this case, they're talking about fusion. So delta H over T. So remember, during the phase transition, the temperature stays constant. So we can take the temperature out front, and then we can just integrate over Q and end up with delta H. So let's see. So for a specific phase transition, fusion, vaporization, they'll all be the same because the temperature is constant over a phase transition. So this self-test, number 6. Oh, okay, so those are fairly easy to calculate, but this next one is slightly more challenging. It says calculate the entropy of vaporization of benzene at 25 degrees from the following data. The temperature at which it happens reversibly is 353.2. Delta H evap is 30.8. The heat capacity of the liquid is given, and the heat capacity of the gas are given. So we want to think that we need to create a cycle. So in order to calculate entropy, all your steps have to be reversible. So when we look at benzene vaporizing down here at 25 degrees, this isn't reversible. So we can slowly heat up benzene in a reversible way, and the entropy would change by Cp of the liquid times ln of T2 over T1. Then we can carry out the phase transition at its equilibrium temperature, and then we can cool it back off. So because it's a state function, we can add these 3 steps together, and we should be able to get this one. So let's see. So for the first step, the heat capacity of the liquid is 136.1 joules per k-mole. We're going up to 353.2 from 298. So this is T2, T1. The delta H for vaporizing benzene is 30.8, and I just changed it into joules to be consistent with these joules. And you divide it by the temperature at which it happens in equilibrium, so that's this step. And then we have to cool that gas back down. So this is the heat capacity, molar heat capacity of gaseous benzene times T2 for this step is 298, T1 is 353.2. You add those all together, you get positive 96.5. So if your process isn't reversible, you may have to use a little bit of thought in order to figure out a way to do the same thing, but to do it reversibly. So when we talk about the system, those are the equations that we'll use. And now when we talk about the surroundings, it's the same concept, but it's a little easier because in the surroundings, we think of like a reaction taking place in a beaker, and the surroundings is the rest of the entire universe. Well, a little bit of heat flows in or out of the universe. Its pressure doesn't change, its temperature doesn't change, and all you have to think about is to make it reversible is to do it slowly, and you know the temperature will stay constant. So when you integrate this last equation, you get this equation because T is a constant for the surroundings. T is also, you can drop the reversible because the surroundings isn't undergoing a volume change or a pressure change. There's nothing going on except the heat being released into it. And so it doesn't really matter how the heat's released from the system. It's not going to be irreversible for the surroundings, which is a little hard to think about, but if you think that through carefully, because of its size, that will make sense. So we can change our equation at the bottom here where it says reversible to the Q of the surroundings divided by T. And the Q of the surroundings is going to be the negative Q of the system. And you'll divide that by T to get the delta S of the surrounding. So let's do one more self-test, page 98. So suppose you have a small reptile and it operates at 0.5 watts. So that's the energy output, 0.5 joules per second. What entropy does it generate in the course of a day in the water in the lake that it inhabits where the temperature is 15 degrees? So that's pretty easy to think. That little reptile can be generating 0.5 joules per second, but it's not going to change the temperature of a huge lake. So the temperature will stay constant. So the heat that the little reptile is generating is the 0.50 joules per second, which is a watt. 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, because they're asking about how much does it change the entropy in a day. And so this is the heat that it gives off. And all you have to do is change the sign because the lake absorbs the opposite amount of heat. So this is given off by the reptile, absorbed by the lake, divided by the constant temperature because that little reptile doesn't change the lake's temperature. And I got 150 joules per K would be the entropy change of the lake. So next we're going to talk about absolute entropy in section C, but we should have enough information from this topic in order to calculate any entropy we need to calculate.